Good afternoon, everyone. How are you all today? I got a real quick question. How many of you are world cruisers? Oh, all right. The reason I ask that is because Susie and I will be leaving the ship shortly. In fact, this is the only talk I'm going to be giving for this leg. But wait, we will be back in Los Angeles to take you back home to Miami. So there will be some opportunities there for you. And again, if anytime you have questions that you want to ask about ports or you want to ask about my talks and you see us around, please feel free to stop and chat and have a meal or a cup of coffee or whatever with us. And we really appreciate that. Anyway, I'd like to welcome you all to this presentation. Now, to set the stage a little bit for this presentation, I'm not going to talk about Meryl Streep or Robert Redford or even the movie Out of Africa. Instead, we're going to take a look at, I guess you'd call it our geologic world. And today we're going to look at the formation of the continents and the oceans to kind of see how dynamic our Earth is. Africa is forming a new continent, by the way, but don't run out to make a whole lot of real estate investments just yet because you're going to have to wait a while for those rewards to come back, like maybe a million years. We're going to have a little more on that in a minute. Now, this beautiful photograph from space is of the planet that we call home. It was taken nearly 50 years ago by the Apollo astronauts. Imagine that. That was 50 years ago, and in my mind, it seems like it was just, yesterday. Maybe that's because I'm getting older. Anyway, the Earth has a 4.6 billion year history that's driven largely by forces that push and pull the continents and shape of the Earth. And we're going to move forward. We're not going to go all the way back to 4.6 billion years ago. We're going to move forward to a period after the Earth had cooled down from its formation, after the moon had been formed, and the very early land masses rose up from the sea. As the lands finally spread apart, seas started to widen and deepen, and the water began to control the atmosphere and the climate. The oceans filled with plants and animals. Well, okay, so how did all of that happen? It all started with one large landmass, and I'm not talking about the very, very beginning. I'm talking about a landmass that was known as Pangaea. Now, it existed during the Paleozoic and the Mesozoic eras, beginning about 250 million years ago. So we've taken a pretty big leap forward already. Now, Pangaea wasn't the first supercontinent to form on Earth, but it is the one that geologists today usually identify as the starting point, if you will, of the breakup of these land masses into smaller continents that we know today. Of course, some of those continents, as you know, aren't all that small. In 1908, a German meteorologist, the guy in the evening weather that points at the map, that's what this guy was. His name was Alfred Wegener. And he named the supercontinent Pangaea. He coined that term from the Greek words that meant entire and earth. Wegener believed that Pangaea once covered an area basically from the South Pole to near the Arctic Circle. And he theorized that it subsequently rifted or broke apart. Pangaea first broke into Gondwana and Laurasia, then into the continents that we know today. An Austrian geologist named Edward Suess, not the guy that wrote The Cat in the Hat, this is a different Edward Suess, called the landmass that made up South America, Africa, India, and Australia Gondwana. That was way back in 1895, well before Wegener. He named Gondwana because of some of the early rock formations that he studied, and those were first investigated in a part of the Indian continent or subcontinent we know today, and the Gondwana is an area within India. In 1927, Alexandre Dutoit wrote of the split between Laurasia and Gondwana. He said that happened about 225 million years ago, and it took about 100 million years to complete. So things don't happen, like that. It takes a little bit of time. He named Laurasia by combining the terms Laurentia, which was an ancient term for North America and Eurasia, along with Asia. He suggested that the two supercontinents further broke apart into the land masses that exist today. Suess based his conclusions on an extinct fern. Its name is Glossopteris. Hard to say. Say that about 3 times real fast. and it came from the ancient Greek. The name means tongue because the leaves themselves were tongue-shaped. This fern's fossils have been found throughout South America, Southern Africa, India, Australia, and even in Antarctica. Amazing. A fern that once lived in Antarctica is also found in India. Alfred Wegener raised very similar questions, and among them were, why are there coal deposits in Antarctica when those are created from plant debris from tropical jungles? And how did similar plant and reptile species show up on both sides of very wide oceans? The flying fox remains common to most of the continents that were once connected. Wegener himself saw similarities in rock structures and fossils that are found on coastlines in South America and in Africa. Other parts of the world that were widely separated featured similar findings. He theorized that it wasn't possible for the animals, plants, or rocks to have moved across such vast bodies of water. Of course, being a meteorologist, he didn't really understand that rocks can't swim. Actually, he did figure out they couldn't swim, and there's very few rocks that are available in the world that even float. And yes, there are rocks that float. Most of them come about as a result of volcanic activity that blows pumice up into the air and it gets captured in the rock and it comes down and it kind of floats until it runs ashore and becomes sand. Anyway, we'll move on from that. Basically, he decided in his mind that because these things just couldn't move across those vast bodies of water, the land itself had to have moved. Well, these scientists weren't the first to see the connections. Back in 1596, not too long after Columbus got lost and found his way to North America and to the west, a Dutch map maker by the name of Abraham Ortelius thought that the Americas were torn away from Europe and Africa by earthquakes and floods. Ortelius speculated that the coastlines of the continents fit as if pieces of a jigsaw puzzle. And you can see in this version of his map, if you look at South America and Africa, there's a pretty close fit. Even today, if you look at maps of the two continents, you can see a very close fit. Also, if you look at North America and basically Europe and the northern part of Africa and so on, you can kind of see you could nudge those back together again, kind of like a little bit of a jigsaw puzzle, even though the northern part is a little more fragmented and didn't quite fit together as cleanly as did the south. In 1858, an Italian geographer by the name of Antonio Snider Pellegrini drew this map. He was influenced by the earlier work of Ortelius, and he furthered the concept of how South America and the African continents once fit together. In 1927, Alexandre Dutoit wrote a geological comparison of South America with South Africa. His work was supported by studies that he had done over in South Africa for over 20 years. And in it, he strongly supported Wegener's theories. As a matter of fact, he was one of the very first of the geologists of the time who even thought that Wegener was anything but crazy. The coincidence between the geology of South America and Africa is one of the clearest confirmations of the continental drift theory. Well, as I kind of alluded, Wegener was attacked from the very beginning. Everybody thought this guy had gone over the edge. Geologists at the time really believed that the Earth's crust was simply a very hard, rocky plate. They thought that the land was changed only by things like weather and erosion and earthquakes and volcanoes. They just couldn't come to grips with the idea that things could move around. They couldn't accept Wegener's theory that the crust was made up of movable and moving plates. The movement of land masses was caused by what Wegener termed as continental drift. Now, this animation shows pretty much his concept of continental drift. And I have to tell you, if it was that fast, it'd be really tough to stand up anywhere in the world. So it's not that fast. We're talking about a sequence here that might take, maybe 100 to 150 million years. so you don't have to worry about getting knocked off your feet just yet. Anyway, Wegener theorized that the crustal plates formed hundreds of millions of years ago and that they've been drifting about around the Earth ever since, and they're still drifting about today. In 1930, Alfred Wegener was lost in Greenland, and most likely he froze to death on an expedition. Soon afterward, his theories were finally verified. And although we've seen several scientists that came before him, it was really Wegener who put it all together. His idea in the early 20th century was a very major breakthrough in our understanding of the Earth itself. He believed that the study of how it was formed and how it changed over time required all the sciences, not just geology, not just meteorology, not just oceanography. He turned to all kinds of disciplines from anthropology to seismology and even off to zoology to verify his concepts and theory. Continental drift can best be explained by understanding the Earth's basic composition. And scientists today describe it as having a crust, a mantle, and a core. The crust, or the outermost layer, that's the thing that we're most comfortable with, that's the thing we stand on, is rigid, brittle, and relatively thin. The crust under the oceans is maybe 3 miles thick. It's not very big, it's pretty thin, it doesn't have to hold up much but a bunch of water. Under the continents, it averages, maybe about 7 times that. So you're talking about maybe 21 miles thick, and under some mountain ranges, the crust could be as much as 60 miles thick. Now you got to remember, that's the Earth itself is balancing itself. It has to be able to support all of that heavy weight that's up there on those mountains. A lot of those mountains were formed by the Earth itself, so it has to compensate. Beneath the crust is the mantle. Now the mantle is a dense, very hot layer of semi-solid rock, and it's about 1,800 miles thick. Now in this layer, both temperature and pressures increase with depth. So the further down you go, the hotter it gets. Actually, if you ever go into a very deep gold mine, or any other kind of mine for that matter, you will realize that it's much warmer when you get down near the bottom of that mine, very deep into the earth, than it is up on the surface. And it's kind of counterintuitive to some people. They think, wait a minute, I'm going down on the ground, it's got to get colder. It doesn't. It gets quite a bit warmer. The upper layer of the mantle is much more cooler than the lower levels, and it's much more rigid, so it tends to be kind of a little bit of a flexing thing that happens in the mantle itself. At the center of the Earth is the core, and it's twice as dense as the mantle itself. Now the core, just because we got to have something to talk about, has 2 parts. There is a liquid outer core and a solid inner core that consists mostly of iron. Actually, it's that inner solid core that gives us our magnetic field. That magnetic field protects us from solar radiation and all kinds of things like that. It also allows us to have magnetic compasses and for Boy Scouts to have their little compass so they don't get lost. Okay? Well, even though the center of the Earth is hot, and it's really hot enough to melt iron, the inner core itself basically doesn't melt. Literally, it's the pressure that's in there that creates the heat, but it's also that pressure that keeps the iron solid. Now, what's all of this talk about plates way back up on the top? Well, the plates are just large chunks, if you will, of the Earth's crust, and they make up the whole Earth's surface. As I kind of said earlier, some of the plates are under the ocean, some of the plates make up the land that we walk around on. Today, there are 12 very large plates and many very small plates. So there are a lot of different combinations that you can look at. Now, they developed very early on in that whole 4.6 billion year history of Earth. And then they kind of have been moving around. To give you an idea of what they can do, they can collide, they can pull apart, they can slide alongside of each other. And I guess it all depends on whether they consider themselves to be good neighbors or not. The drifting of those plates is caused by a thing called plate tectonics, which comes from the Greek term to build. Plate movement may cause the things that we all have come to know and love, earthquakes, volcanoes, tsunamis, and all those wonderful, joyous events that the humans look forward to. Plate movement may also cause other events. But for the most part, that's the big things that we are most familiar with. Now, our continents are driven largely by forces that push and pull the land constantly. They are always on the move. Some of that movement is caused by just the rotation of the earth. Some of that movement is caused by the gravitation of the moon, some of it by the gravitation of the sun, and some of it just because the continents want to move around. Now, shown here is a graphic of the oceanic plate, and this is where a plate is being pushed beneath a dry land or a continental plate. And that's usually what happens when one plate comes up to another. As I said, they can run into one another, slide under one another, slide alongside. This particular process is called subduction. Subduction basically means one is being pushed under. Now, the plate material is pushed back into the mantle, which comes up basically under the Earth's crust. There it gets heated, and very often that heated material that got pushed down comes back to the surface as a volcano. So in the area where you have a lot of these subduction zones, you will also have volcanoes. As an aside, you also have earthquakes when you have subduction, because every once in a while that subducting plate will kind of get stuck. And when it gets stuck, it kind of builds up pressure, and over time that pressure will continue to grow. And then finally it will break, and when it breaks, you have an earthquake. Now, to give you an idea how an earthquake works very quickly, if you took a green stick, preferably a stick that you could bend, you take a green stick and you bend it and you bend it and you bend it. At some point in time, that stick is going to break. Well, just as it breaks, there is a vibration that you will feel in both hands as that stick fractures. It's exactly the same thing that is an earthquake when the earth lets go of one of these stuck subduction plates. When Gondwana tore apart from Laurasia and Africa, the Indian plate started to, Africa and the Indian plate started to move apart. Anyway, the Indian plate basically started to move northward toward the Asian plate. And it was accompanied by massive eruptions of basalt lava that occurred in all over Antarctica, Australia, South America, and all of those started to separate away from Africa. There was a huge eruption about 65 million years ago that occurred as India passed over the Reunion hotspot. That's a place out in the Indian Ocean. Now, scientists believe that that is when India dumped off Madagascar and the Seychelles. You know, you're traveling along and you got excess baggage, well, you just let it go. That large eruption that broke those land areas apart also formed what we know of today as the Deccan Traps. Now, trap is a Dutch word for stairs, and when you see these things, they look like a big staircase. They're located in the middle of India, and they're one of the largest volcanic features anywhere on Earth. When these traps formed, the lava flow covered an area half the size of present-day India. That eruption also coincided with, among other things, the extinction of the dinosaurs. So there is some, I guess, scientific consideration or speculation anyway that the two events were related. India could now move faster. Remember, I told you to get rid of all that excess baggage, and they lost all the dead weight. It was now charging north at a rate of about, it was the fastest it's ever been kind of figured out by the geologists, something in the order of 7 inches a year. In geologic terms, that's really fast. You know, it's faster than I move sometimes. Anyway, when the plates finally meet, one doesn't go under another sometimes at the point of contact, and they just kind of push against each other. In other words, when the plates are drifting about, they kind of crash into one another, a little head-on sort of thing. Well, when the Indian and Asian plates collided, they formed the Himalayan mountains. The Indian plate slowed down a lot. I mean, it went from 7 inches a year, just like that. Really slowed it down. Didn't stop. And the Himalayan mountains are a product of the Asian and Indian plates having that little fender bender. Today, the plates are continuing to move. India is moving north still at about 2 inches a year. And as a result of that, the Himalayan mountains are still growing. So the pressure that's coming from that big landmass moving up is pushing up, pushing up, pushing up. So, well, how did that happen? Well, the whole thing really started as India was moving across what we know of today as the Indian Ocean, uh, and they went across a hot spot. A hot spot is basically just a place where in the mantle there's a plume of very, very hot lava, and this was in the middle of kind of a tectonic plate area. Now here the molten lava or magma that's coming up from the center of the earth pushes up against the bottom of the plate. And when that happened, as the plate moved across the hot spot, it kind of bubbled up and pushed things up out of it. And there are a lot of these hot spots around the world. And we're going to talk about just a few of them. We mentioned that big eruption that occurred when India turned Madagascar and the Seychelles loose, and that happened at what we know of today as the Reunion Island hotspot. So as it was going across, it went across the spot where Reunion Island sits today. The mid-plate Reunion Island volcano is one of the most active of all the volcanic sites anywhere in the world. Eruptions there have lasted for 30,000 years. So it's been a pretty active thing. And the last major eruption, the last significant one, was back in 2010, and that was created again right at that hotspot. Now the splitting of Gondwana and Laurasia from Pangaea created this hotspot out in the middle of the Indian Ocean. And just out of curiosity, it's not a whole long ways from where we are right now. In fact, we're going to be passing you guys are going to pass a lot closer to it than I am. But anyway, I'll think of you as you're going by. Now, this is a cross-section of the Earth at the Hawaiian Islands. It's one of the easiest ways to think about how a hotspot works, and it's an excellent example of how islands are formed over these hotspots. When a weak or a thin part of the plate passes over the hot spot, very hot, very liquid lava sometimes will break through that plate, and then eventually the plate will move off. Well, one of the things that happens in Hawaii is this is an ongoing thing, and every island in the Hawaiian chain, all the way from well past Midway, all the way to the islands that we know of as Hawaii today, all were formed by this one hot spot out in the middle of the Pacific. Well, anyway, as the hot spot cools, volcanic activity at the hot spot ceases and the plate continues to move off. In the particular case of the Hawaiian Islands, the plate is moving which direction? The plate is moving off to the northwest. It's heading toward the Aleutian Islands. And then eventually it'll come to another weak place in that plate, and another volcano will come up, and another island will be formed. In fact, there's one that's just a little southeast of the main islands of Hawaii right now that's still below the surface, and it's going to come up in a few years, and then the real estate people will go crazy with all this new territory that they can sell. It'll be initially very good beachfront property, and you'll be able to plant your own plants. Anyway, the activity just is continually ongoing, and those new islands just continually form. And it's one of the most dramatic examples of plate movement. You can actually go on a map of the Hawaiian Islands and all the islands that go all the way out almost to Russia, and you can just kind of plot the movement of that plate over time. This is another example of volcanic islands that were formed in mid-plate. The Madeira and the Canary Islands and Cape Verde also are part of what's called Macronesia. The Macronesian archipelago is about a 1,700 kilometer or about 1,000 mile long line of volcanoes. And that happened as the African plate moved over a hot spot. Now actually the African plate hasn't moved very much in all of geologic history. After South America broke free, all it did was kind of turn a little bit. And geologists aren't really quite sure why Africa never went anyplace, but it just kind of turned a little bit and then it stayed there while everybody else moved around. Anyway, most of the volcanic islands around the world are found at the boundaries of these tectonic plates rather than at these mid-plate points. And you can kind of see the Azores up there, and they're not at a boundary. They're at a boundary, they're not at a midpoint. And that's out on a boundary, and those are where the tectonic plates are either coming together or pulling apart. And what happens there is the same thing that happens up at Iceland. The Azores in Iceland were created when the European and the North American crustal plates were being pulled apart or rifted. And that's really another type of that movement. Remember I told you there was a whole bunch of different ways plates interact with each other. Now, when they don't subduct and they don't kind of crash into each other, sometimes things will just bubble up at mid-plate, as we talked about, or sometimes the plates will pull apart. If you go to Iceland today, you can literally put one foot in Europe and another foot in North America. And if you stand there long enough, your feet will get farther apart. Yeah, it might be a while. You will get very old, and your great-great-grandchildren will come to see you before it happens, but it'll take a long time. But anyway, that's why the islands that we know of as Iceland are actually forming, is because it's right on this boundary between two plates. Now, the crustal lands are spread apart, and the seas basically widened and deepened. And when Gondwana Land and Laurasia were separated, the first thing that happened was the Tethys Sea was formed. Eventually, the Tethys became the Indian Ocean, and part of the Tethys also became the Mediterranean. Now, you got to go back and remember, you remember Dr. Seuss, the guy with the, no, not the guy with a hat. Anyway, Seuss was from the 19th century, and he was the one who theorized that the Tethys Sea was what had come into being and was originally these two bodies of water. There are craters on the moon and Mars, basically, that are named for Seuss because he was really so far ahead of his time. Now, the Rheic Ocean formed between North America and the African plates. As those two plates started to pull apart, they became the Atlantic Ocean and the Caribbean. All right, everybody says, okay, so where'd the Pacific come from? The Pacific was all the other water. So as all this stuff moved around, what we see out there as the Pantheist Ocean basically became what we know of today as the Pacific. Now, we promised to look, or I promised, I guess, a look at a new continent that is forming as we speak. So all of you that have broker's licenses, now this is the time to really think about what's going on. There's a new continent that's forming, and by explaining how a continent is formed, you're also going to see basically how an ocean is created. Geologists, by the way, are calling the new continent the Somali Plate. They don't have a name for the continent yet, but they're calling the mass the Somali Plate. Now, the continent is tearing apart basically at the Red Sea up in the north and down to the Rodriguez Triple Point out in the middle of the Indian Ocean. The African, Asian, and Antarctic plates all meet out there in the middle of the Indian Ocean at what we know of as the Rodriguez Triple Point. And you can see that's the star that's in the middle. And those rectangular boxes on this particular chart represent the intensity of the seismic activity that's around those plates. And lately, there's been a lot of new activity up in the area that's circled in red. Now, this is called the Great Rift Valley of Africa. And you can kind of see it in this picture from space. It'd be a lot better if I had better glasses. Anyway, here the plates are basically tearing or rifting apart. And eventually, that rift will fill with water. Fortunately for most of us, the rate of geological processes are pretty slow, so you can't really appreciate it, except for an occasional earthquake now and then. You really don't get a chance to understand it. Anyway, the west side of this new continent is along this 3,700-mile rift or tear in the surface of the earth. And there isn't really a separation of the continents yet. It's just that there are vast bodies of water at both ends that basically is now looking at that land in between. And what it's looking at is, wow, I can go in there. Someday I'm going to make it in there. Well, here's how that happens. It all starts out, if you take a look at the African Rift Valley, what happened there is there's a kind of a crack or a weak part in the surface of the earth. And there's a thing called upwelling, which is the mantle pushes up against the land. And as it pushes up, little ridges start to form. And as those little ridges start to form, they'll build up and build up and build up. And then eventually they'll all cave back in again. But it also pushes the land a little bit further apart. And it will continue to do that upwarping. It'll continue to push further and further and further apart. And every time it drops back down, it starts the whole process over and over again. And this happens over, maybe a million years, maybe a little bit longer. But the structural failure of the rock actually starts to make that rift valley. So if you go to Africa, where we have been, and if you go into the interior of Africa, into the Great Rift Valley, you're going to see exactly that geologic activity. Well, anyway, that narrow valley will continue to grow, and it stretches until it essentially runs the entire length so that it goes all the way across the boundary between the two plates. And it will continue to widen and deepen and widen and deepen year after year. It might only be a little bit each year, but it's going to be a continual thing, always caused by this upwarping of material. And that continues until finally it will reach a boundary where there's water. In this particular case, it will continue until it gets up to the Red Sea and down into the Indian Ocean. And then the new floor, which is now well below sea level, caused by that whole rifting process, all of a sudden the ends of that will breach and it will fill with water. Now you have a new ocean. And as the plates pull apart, the molten rock will break the seafloor, and that becomes what is now seen as a little bit of an undersea ridge. And the more it builds up, the bigger that undersea ridge becomes, and potentially there might even be islands there. Same thing that happened in Iceland, the same thing that happened in the Azores. That mid-Atlantic ridge is a very classic example of this particular force. Anyway, the new magma and molten rock from very deep in the earth will continue, and it will create this new oceanic crust. It's actually pushing the plates apart. So everybody says, okay, well, I understand it's pushing the plates apart. Why isn't the earth getting bigger? Simply because there are other places in the earth where the plates are being subducted one under the other. A classic example here is off the coast of Japan, where there's a huge subduction fault, which is a very deep canyon in the ocean floor. The deepest of all the canyons is down in the Marianas Islands, where you have the Marianas Trench, and that's where the Pacific plate is actually diving under the Asian plate. And that's what keeps the Earth the same size it's always been, give or take a few meters. Anyway, this whole thing, this new crust is causing, in this particular case, in the mid-Atlantic, North America is moving away from Europe. In Africa, the Somali plate is trying to pull away from mainland Africa. Now, the more they pull apart, the bigger the body of water that is now contained between them, and that body of water continues to deepen because that plate movement is continuing to pull further and further apart and making the land more and more distinct. And eventually, over, a couple of million years, that will become a mature ocean, very much like the Atlantic. Over many, 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 many more years, it will start to look like the Pacific, because you're going to have some subductions on both sides where the land is going to be forced down under. And this small ridge might form in the center as magma presses up from within the plate boundaries. And that action over millions of years is responsible for all those mid-ocean ridges that I talked about. Basically, the idea in geologic terms has become known as seafloor spreading. It's kind of like what I feel when I go through the buffet. Only mine's waistline spreading. And basically, it is those ridges and the motions that happen and the formation of these new ridges in the middle of bodies of land or in the middle of water that's kind of proof that Pangaea tore apart 250 million years ago. So it's kind of an interesting phenomena. And when we're traveling around here, it's very difficult for us to understand all of these forces. Now, those of us who are fortunate enough to live on a fault line in California can attest to the fact that these forces work quite well. In fact, even in Japan, they understand earthquakes. A whole ring of fire. I do a whole series of talks on the ring of fire. And the ring of fire, if you plot all of the earthquakes and the volcanoes that have happened around the ring of fire, you can see this large Pacific plate. It's a very distinct ring of several thousand volcanoes and hundreds of earthquakes that occur every year. And it's just proof of all of this dynamic earth, the earth that we live on. Now, as we sail along on this ship, it's really hard to understand and get a sense of the great forces. Some people will go, wait a minute, we had big waves. Well, those waves are just kind of local. They're caused by wind. Tsunamis are caused by earthquakes and volcanoes, but on a ship at sea, you will not feel a tsunami. The tsunami will just be a minor little bump in the water, and the ship will just go across it because it doesn't have anything underneath it to push it up to the height that becomes destructive when it rolls ashore. And as I said, many of the forces that we see on land are hidden very deep beneath the sea. And, you know, for those of us in California, Japan, and a few other places, yeah, we experience earthquakes, but it's not that big a deal, unless you happen to be in one. Anyway, as you're going north from here, and you're thinking about things when we get to Madagascar and we get over, ashore, and you start thinking about those little islands up there, think about the fact that in 1 million years or so, that whole area will be a new continent, yet to be named, but right now it's called the Somali Plate. Now, this is my only lecture, as I said earlier, for this cruise, but you got to kind of give us a break. We've been on ships now for 4 continuous months, and it's time to take a little bit of a break. As I said earlier to all the world cruisers, we'll be back when you reach Los Angeles, so we'll be able to take you back to Miami. And if you have any questions or comments about this lecture or any of my other lectures, you just want to talk about the cruise, you want to talk about 20th century pirates or 21st century pirates, I love to talk about pirates. Anyway, you can meet me out in Baristas. That's the coffee shop outside the main dining room. And I'd like to thank you very much for your attendance today. Have a great afternoon.